This video is a review of Angular Kinetics, Lesson 8. Here we have the definition of a moment, r cross f, where r is the position vector from the moment center to the line of action of force, and f is the force vector. Here we have the scalar definition of a moment. The moment is the moment arm ma times the magnitude of the force, and the direction is obtained by the right-hand rule. The force balance law is Newton's second law. The sum of forces equals mass times acceleration. And the moment balance law is equal to the sum of the moments is equal to the mass moment of inertia times the angular acceleration alpha. This is a simple example of a bicep problem. The forearm is horizontal and holds a dumbbell of weight WB. The forearm itself has a mass WA acting at its center of mass. The muscle force is FB, and the reaction force at the joint is FR. This is the force that the upper arm exerts on the lower arm. Point O is the moment center. D1 and D2 are the moment arms to the two weights, the forearm and the dumbbell. The moment balance law is applied. If it's a static problem, alpha equals 0. Sum of the moments equals 0. These boards show the definitions and the equations that govern the problem. This board shows a more complicated example with multiple muscles acting at the elbow. These boards show the relationship between muscle force and muscle length. We'll look at some more details of this for the muscles in our example. Our problem is to find the angular acceleration of the forearm given these quantities. In this case, the arm is horizontal, that is 90 degrees orientation. The distance from the elbow to the dumbbell is the moment arm D2, 0.3 meters. And the distance from the elbow to the arm center of mass is D1. The forearm mass moment of inertia about its center of mass is given, and the forearm mass moment of inertia about the elbow point O is calculated from the parallel axis theorem. For the four muscles involved in this problem, we have enough quantities to calculate the moments about the elbow. We have the peak force, the length quantities, and the moment arms, and the activation for the four different muscles. Here's the free body diagram, assuming planar motion, constant moment arms, and we're neglecting force-velocity relationships of the muscles. We also assume the upper arm is fixed. Point O is the moment center, and the moment arms are shown by these little blue lines, the perpendicular distance from the force of each muscle to the moment center, O. The next series of notes shows how we calculate the muscle force and the muscle moment about the elbow. Here's an example for the biceps. The peak force is 800 newtons. The force has an active component based on this triangular shape and a passive component based on this linear shape that starts at the point 10. In our case, our muscle length is 11 centimeters. The active component is 480 newtons, and the passive component is 160 newtons for that length. So the total force is known, 640 newtons. Since the moment arm is known, 0.05 meters, we can calculate 32 newton meters counterclockwise for that muscle. Similarly for the other four muscles, the brachialis, the brachioradialis, and the triceps. But notice that the triceps acts on the opposite side of the muscle, and its moment arm, its moment is negative. In other words, it's a counterclockwise moment, whereas all the other three were positive. Here's the moment balance law. The sum of the moments equals the mass moment of inertia I times the angular acceleration alpha. All the quantities on the left-hand side, that is, the sum of all the moments acting, is known. The only unknown in this problem is alpha, the angular acceleration. The mass moments of inertia are known. Here, 1.5 kilogram is the mass of the forearm, 9.81 is the acceleration due to gravity, and 0.15 is the moment arm for the forearm. Similarly, for the barbell, 10 kilograms weight, 9.81 meters per second squared, and 0.3 meter moment arm. So those are contributions to the left-hand side. Here's the sum of the mass moments of inertia, and we calculate alpha. In a different problem, the problem we're going to look at for our optimization study, the muscle forces are unknown, and that presents a problem with more unknowns than we have equations, and we can't solve it using these methods.